Hello and welcome back to Tomography. So I've been caught up with a lot of grant writing and paper writing this past few weeks, and I haven't been able to get down to the brass tacks of Matlab for our class yet. So part of the reason why is because I need to sit down and actually learn what we needed to do, because usually when I do this sort of thing I always do it by hand, but in this case, it's valuable to have some of the tools available from Matlab, and so let's go ahead and talk about that. So what we're aiming for right now is we want to have the image processing toolbox from Matlab. So you can get this as a USF student from the USF software store, download Matlab, and make sure that when you're installing Matlab that you include the image processing toolbox. If you do that, then you get the Radon transform and inverse Radon transforms that filter back projection, and also the automatic generator for the Shep-Logan phantom. This is all fairly handy, and in this lecture what I'm going to do is I'm going to go ahead and show you how to go ahead and do a Radon transform and inverse it. Now for the project, what I want you to do is a little bit different than this. So what I'm going to show you is how to sample your phantoms the way that they do with the Shep-Logan phantom, and so that you can go ahead and use do that in a pinch. But for the examples I want you to do in class, for the first project, is I want you to go through the textbook on medical imaging, the one that is part of the undergraduate series. I'll put a thingy around, and implement all of the Radon transforms of ellipses, squares, and the rotations and shifts of all those. So you can make up your own phantoms, and you get an analytic form for what the sinusoid is. And in that case, I would like you to take the give me a plot of the sinusoid, the Radon transform of each of these, and so I can just go through and press play, and then have a whole bunch of figures of a bunch of shifted different versions of the ellipses and squares and whatnot. But in this case, I'm going to show you how you can do this from a sampling point of view, just so you have some sort of a benchmark to make comparisons with. Doing the sampling point of view will actually give a worse Radon transform, but maybe it would still be good here, of each of these shapes that we're talking about. Alright, so let's go ahead and start talking about it. So over here, what I have is I have the loaded up the Shep-Logan phantom. So this is built into the image processing toolbox, and it will automatically make the phantom for us. And it puts this into a matrix form with a bunch of different values on the matrix. And then you can basically take any of those, that matrix full of different values, and you can take the Radon transform of it. Basically what Matlab does is it just shoots a whole bunch of lines through there and takes a bunch of numerical intervals. And it does this at these angles. You don't have to have this if you want to automatically choose it. I chose basically 0 to 179, basically one short of 180 degrees. So these are in degrees, by the way. And then I can go ahead and do a back projected Radon. And so first, let's go ahead and take a look at what happens when you don't do filter back projection, but just regular back projection. So here I have 3 different ways of showing it. Each of these are actually end up being matrices, and so I'm telling Matlab to treat these as if they're images and just show me what you get. So so let's go ahead and push play. So here is my Shep-Logan phantom. Here is my Radon transform, and so it's looks like, so here it's going to be in angles, and so this goes from 0 to 179, and I think it's going up to a full 1024, which is what I set my Shep-Logan phantom to be. So there you go, and then I'm telling it to take the inverse Radon transform of that. And so this is just using back projection, and you see we have an immediate problem. We didn't get anything back out of it. But here's a cool thing. If I go ahead and set this to remove this, and it does automatically the filter back projection, you can see I've actually had problems a second ago. But if you go ahead and press play, there we go. this nearly comes back. Using the same samples, exactly the same, it was able to get nearly a perfect reconstruction, which really motivates all that stuff we're talking about with the Fourier transform. It's ultimately going to enable us to do this sort of thing using the FFT and other things. And so it uses the same data that we had from sampled here. So basically this is the original phantom, this is the radon transform of the phantom, and then over here is the filtered back projection. And so this does considerably better than what this guy did over here. We do still have a little bit of noise coming in here, and that's to be expected. It's only 179 samples, in angles, and more as we shifted it. But yeah. So we got nearly a perfect recreation of the image, or before we got nothing. So that really encourages us to continue down this path of the Fourier transform. We'll get to FFT and other things like that in maybe 2 or 3 lectures from now. Okay, let's see. So let's see what things we can adjust. Putting this back to none, and let's just increase the number of samples. So I'm going to go 0.5, so doubling the number of samples I'm taking here. Let's do 0.5 to here, and see what we get. Still nothing for the unfiltered back projection. This is looking a little bit wider, which is nice. And if I go ahead and put in this, let's see if we improve things. Yeah, okay, so now that noise is almost entirely gone as we increase it. There seems to be some little band here, but it's not bad. Okay, so as we take more samples, we do better. And so let's be ridiculous and put 0.1 and 0.1 here and see what we get. It's going to take a little bit of time, but there we go. All right, so now this is the radon transform of that, and that's what we got here. And yeah, that's what we got over here. Okay, cool. Let's see. So there we go. So this is just using the straight things straight out of Matlab. Now let's go ahead and make up our own phantom. So let's take a look at what the Shep-Logan phantom looks like. We're just going to change it down to, say, 32. Or let's actually just change it down to 16. So now we have a ridiculous number of angles, but only 16 in height. And so you can't even see the Shep-Logan phantom here. If I see if we can... It's not doing very good as far as increasing that. But basically, it's a tiny little Shep-Logan guy we have in here. And ditto over here. It's really, really tiny. Okay. So, but if I go ahead and plug in Shep-Logan and see what it is, as far as matrix, that's what it looks like. So these are all my blacks, and then these are grays. We have a couple of whites in here at 1, and so it's a gradient between 0 and 1. Okay. I actually have a feeling if I go back to the back projected, I can get something out of it this way. So using the knowledge that 0 is black and 1 is white, I'm betting when I didn't do the back projection, I got something else. I'm guessing it's saturated at white somewhere. So if we go ahead and, right, so we get whites there. And let's go ahead and take a look, and maybe we can adjust these images. So if I take the maximum of the absolute value of back projected radon, let's see what we get. Yeah, it's 298. So what I'm going to do is I'm actually going to take, and let's also figure out what the minimum is. Min 91. Okay, so what I'm going to do is I'm going to shift and I'm going to shrink it. So, so then we can actually see what the proper back projection is. So that tells us how good the filtering did actually. It took this thing that was normally back projected and it was scaled up way too large to 200, and you had a base of like 91, and it put it between 0 and 1. And that's pretty awesome. So right, so what I'm going to do is I'm going to take this guy, I'm going to shift it back to where we like. So I'm going to take the minimum of back projection here, and then I'm going to take the same guy and I'm going to divide it by the maximum. So max absolute value of back of the same guy. There. All right, now let's see what we get. Okay, so initially it really was just a scaling problem. So we do get something out of this, but it's not very good. And you can see we also saturated on the radon transform itself, and so we can correct that in the same manner. So I'm going to take the radon transform, and let's go ahead and do this normalization. So minimum of radon transform, and then we're going to have the same guy and take that guy and divide by the maximum of the absolute value of that. There. And boom. Should give us better pictures. There we go. There we go. That's the sinogram that I wanted to see. So, so the last one ended up being way oversaturated. The values got to be way too high, and so so it just maxed out where we wanted. This is much better for display. Okay. So, and then finally, yeah, we already saw that the taking out the filtering already did better. There, okay. So now we have everything behaving like it should. Okay, so so now let's go ahead and make up our own phantoms. So f sample. All right, so I'm gonna make this first function. It's a 2x2 function, and I'm just gonna put x in here. And basically what I'm gonna say is that I want this to be the maximum of, say, 0 and well, let's do an indicator function for this. And so let's see, I'm going to basically say that we're going to have x of 1 squared plus x of 2 squared, and say divided by 2 is less than or multiplied by 2. Say multiplied by 5 is less than 1. All right. So this is going to give me sort of a logical answer, and I think I can convert that to double. So let's just test this out. So I am going to say x is equal to 0.01 comma 0.1, right? And so that's my x, and let's see, logical 1. So can I take double my answer? There we go. Okay, so let's take that. So it's going to give me either a 0 or a 1 that is a logical quantity, but we want to be able to use it for inputting into a matrix, so I changed it to double. So what I can do now is I'm just going to make up a field of numbers. I'm just going to go ahead and sample it there. So it's going to be, say, my x is going to be negative 1 to 1, and let's go 0.1 samples. Yeah. Let's say 0.1, and let's actually just change this to be 2. All right, y is going to be negative 1 to 1, sampling from, etc. Yeah, okay, so we can actually just not worry about that. Now I'm going to set up a grid, and so this is mesh grid, and of x. And this is typically what you do when you want to have a field of numbers that you can basically take Cartesian coordinates of. All right, so now we're going to make a z, and this is going to be same as this zeros that are the same as the size of x, and now let's fill it in. For I is equal to 1 to length of x, and for j equals 1 to the length of x. Basically, we're going to have z equals z of ij should be equal to f sample at x ij, and say y ij here, and that should be good. End. So let's go ahead and take a look. Boom. Oh, sample. All right. Oops. Still had all the other code in there. Didn't mean to have that. All right, but let's see what we got out of this. So we got, well, actually I can go ahead and change this guy out here, and call this new phantom, and I'll just call that Z. Okay. Now let's go through here. I'll put that in there, and then what we get? Boop. So new phantom is way too small to see, so let's change this to being 0.001. And the other guys, let's see. Whoop. Alright, so now it's taking a lot longer. It is sampling basically a 10,000 by 10,000 thing. So we see that this function, it gives me a perfect little circle, right? And this radius is 1/2. It's because I changed the 5 to a 2 here, and so it's going to give me a circle radius 1/2, and so it gives me something to take the radon transform of. Now we saw before in lecture that basically this is what we should get out of the radon transform. At 0, it should be at its highest peak as we go through taking lines here. So this bit here, each one horizontally we're changing the angles of the line, and so basically we're going to be taking slices right down the middle, and so that should be constant because this is symmetric about the origin. So what I can do is I can even shift it up by 1/2, 0.5, and see what happens. Okay, so now we get something more like what we expected. So I've shifted it, and now we basically have this sinusoid going in here. We have another sinusoid going in here, and that is again something we saw out of the out of our lecture. So now I've shifted this by 1/2, and so now it's starting to poke out a little bit, and yeah, I keep showing this. I don't mean to do that. Here's a trick: that circle we keep showing is actually a filtered transform. And so if I change this from Shep Logan to, say, new phantom, they actually get a comparison to how the inverse radon transform is performing. Pretty damn good, honestly. Give it a second. There we go. Okay, so here we go. So here's the original, unfiltered. Then you take the inverse radon transform. Now we chopped off half the circle, so it's not going to be perfect. And so we get this. And then there we go. There's recreation, even with that imperfect information. We have a little bit of aliasing up here and here, but overall it's doing pretty good. Now let's go ahead and let's dramatically decrease the size. So I'm just going to say 20. Let's see what we get. There we go. So here we go. So basically we shifted it up. We end up getting this band out of sort of like a sinusoid. And here's the filtered, and here's the unfiltered. The original rather, not the unfiltered. If you want to see the unfiltered, we can just go ahead and put in none. And let's see what we get. Boom. So with unfiltered, it's pretty blurry. It's like looking at the sun on like on a cloudy day, you know. And yeah, and so the and basically this is the original. So so the filtering does a tremendous job at recovering the image, and that's why people care about it so much. So here's a band, and just real quick, I can show you what it looks like when we shift horizontally. There. What do we get? Just give it a second. Okay, so I shifted it well outside of the realm where it should be, but now we get sort of a minus cosine thing going on over here. So we're actually only a half circle left because I shifted all the way up to 1. That's probably too much, and so let's shift it over to 1/2. This will be the last one I show you. But you can use the same sort of idea in order to get examples for squares and whatnot. So yeah, there we go. So okay, but yeah. In any case, so then that's how you use basically these the inbuilt radon transform and inverse radon transform code inside of Matlab with filtered and unfiltered projections. Here we see the filtering actually did a really good job at recovering the original image. Even for a little while with this sample thing, we were actually looking at the filtered back projected version rather than the original. And so there. Something that's interesting that we should so something I want to talk to you about is the project. And so here I would basically like you to make up your own radon transforms of, say, circles, squares, and ellipses and whatnot, and all of those instructions and examples are all in the textbook. And I basically want to be able to give me I want you to give me a whole bunch of examples of an ellipse, a circle, and a square, and maybe a combination of one or two of them. And I want to basically just pull up Matlab code from you guys, press play, and then I would like it to just give me the radon the original function plotted, just like we plotted this one here, but then give me the analytic version of the radon transform and plot that. And that's more or less the first project. And this will give us a nice little benchmark to see how other numerical routines that we try, how close they get to the pure radon transform given these phantoms, and that's the whole point to a phantom. So then this will be the first project, not too complicated, and we'll increase in sophistication as we go. We might need some techniques from numerical analysis, and I'm teaching that class right now, and so later on I might actually just link you to some of those. But for now, let's get you started, and thank you for being patient with me. It's been a rough semester.